Hey everybody, it's Ribley back again. Today we're going to talk about the topic referred to as implicit differentiation. And there's a problem. As we've said before, we know that calculus is the study of real valued functions of a real variable. In other words, you give me a function, I put a real number in, I get a real number out. The real valued function means that real numbers come out. A real variable means you stick a real number in. And then that thing has to be a function. It's got to be f of x. So if I've got myself, say, a conic section like a horribly drawn ellipse, I've got a real problem here because it's not a function. This thing cannot be written as y equals f of x. However, it should be relatively obvious that this guy has tangent lines. However, if you look really close, where we get into trouble with our derivatives, with our slopes of tangent lines is, let's say that I grab this point right here. Well, if all I'm looking for is a slope of a tangent line and all I'm given is an x, then that x value will correspond to 2 lines tangent, which explains why it can't be a function. Its derivative cannot be a function. However, we may still want to be able to take a derivative of this thing. We may still want to be able to find a point on this ellipse that has, excuse me, that has a tangent line, because clearly it's got tangent lines at every point except where the tangent lines are, of course, vertical, and I reckon those are still tangent lines, aren't those? So let's come up with just an ellipse and figure, let's see. Let's keep it, we're going to keep it, let's do a circle. So I'm going to do x, ooh, I don't like that color at all. Let's get rid of red, makes me angry. Let's say, for example, we know that a circle is just a very special ellipse, right, where both foci are at the same point, which is at the center. So let's take a circle of radius 2. So I've got x squared plus y squared is equal to 4, right? And I want to figure out the equation of the line tangent at, let's do at the point 1 comma root 3, okay? So that's my point. This is my equation, but I don't have a function. Now, I reckon if I wanted to, I could solve for y. I could say y is equal to the positive square root, because that's clearly going to be in the top half, right, of 4 minus x squared, and then take a derivative that way. But there's a more clever way to do this, and it's going to seem like magic at first, but bear with me on this. So I got something on my magic marker over here. Let's see, x squared plus y squared equals 4. It's called implicit differentiation. And what it really reinforces is the fact that this operator, this take the derivative of thing, is not just a command. It's an algebraic and geometric construct. So let me explain in the vernacular how this thing works, and then I'll show you a little more algebraically that we've actually been doing this the entire time. Okay, now here's the way it works in the vernacular. What this thing says is, take the derivative of something with respect to x. Remember, this guy right here always tells me what I'm taking the derivative with respect to. So if I take the derivative of x squared with respect to x, I get 2x. That's easy. Now, here's where I get into trouble. If I take the derivative of y squared with respect to x, well, I can't do that. However, what I can do is say, all right, what I'm going to do is I'm going to take the derivative of y squared as though it's just a function of x. However, I'm going to leave an algebraic footnote that says, okay, this guy right here says, I took the derivative of this, but I cheated. I treated it as though it was a function of x. That's the algebraic construct. All right. Now, this is going to equal 0 because the derivative of a constant is 0 as always. Now, remember, dy over dx is just the derivative of something, right? In this case, y with respect to x. And we're being a little disingenuous insofar as we're saying that we're taking the derivative of y as though it were a function. But it's not a function. It doesn't work that way. And I'll show you what happens. It algebraically plays out. So we aren't being as disingenuous as it may feel. If I solve for dy over dx, well, what do I get? I subtract, I get negative 2x divided by positive 2y. And this is equal to negative x over y. Is it not? Now, look, what this says, clearly negative x over y is not a function of x either. So what we have is it says, okay, while you have a derivative, and sort of algebraically it looks as though we've got a derivative of a function, if we want to use said derivative, notice that I have to have a point. I have to have a point. I can't just plug in an x value. So if I've got my circle of radius 2, let's go terribly drawn circle of radius 2, and I'm going to go out 1 root 3, and I've got that point right there, right? This is the point 1, comma root 3. If I want to be able to determine the slope of the line tangent there, then I need both the 1 and the root 3 to make that happen. Now, the way that's sometimes written in this Leibniz notation is I drop this guy down, and then I say xy is equal to 1 root 3, just like that. And this is a good time for us to sort of review some of the notations for derivatives, but I'll do that here in just a sec. So I plug in 1 where I see an x, so I get -1, and I plug in root 3 where I see a y, and I get root 3, and that's the slope of the line tangent. If I want the equation of the line tangent, that's easy enough, right? I just go y minus root 3. I'm going to use point slope because I wasn't told to do anything else, equals -1 over root 3 times x minus 1, and I'm done. All right, now a quick review of the ways in which we can talk about derivatives. Remember, if I wanted to, I could say y primed at a, I could say f primed at a, or I could do dy over dx at x equals a. Now in this case, what I have here is I have to have a point. I have to have a point to be able to make this thing hum. So, and that played out when we took the derivative. So we shouldn't get confused as to whether or not we took a derivative of a function or if we took a derivative of a not function, because if I take the derivative of a not function, I will get a not function, right? I will get this equation where I have to plug x's and y's in as opposed to just x's, okay? Now, I'm going to prove it real quick over here. Notice, let's make sure that we get the same answer. Had I used this function, which is just the top half of the circle, the horribly drawn circle of radius 2, what would I have gotten? Well, y primed is equal to, remember this is the square root of blah, so I get 1 over 2 root blah, which is 4 minus x squared, times d blah, which is 2x. Oh, don't disrespect thy negative. There's a negative there. Cancel, cancel. And then if I go y primed at 1, then this is going to give me -1 on top, right? Divided by the square root of 4 minus 1, which is root 3. Hallelujah. And you may say, well, Ripley, why don't we just do that every time? You know, I'm comfortable with functions. I like functions. These relations, they're scary. Whoa, 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 careful. What if I have something like this? What if I have x squared plus 4xy minus 3y squared is equal to 1? And I want to take this thing's derivative. All right, well now I can't solve for y. There's no way for me to physically solve for y. This guy ain't a function, and it's not something cute where I can define some aspect of it. Throw this into your Desmos and see what it looks like. That'll be pretty interesting. I'll bet it looks sort of hyperbolic. That would be my guess, okay? We're not going to do that because it's not really important. So here's what we do. We put the whole thing in parentheses, and this notation says, hey, I'm going to take the derivative of everything here as though, I'm going to treat it as though it's an x, okay? Well, that's not scary for x squared, right? I get 2x. Now, I got to be careful here because this is a product. I'm going to treat this as 4x times y. If you wanted to, you could say that this was x times 4y, or 4 times xy, but I'm gonna notice that this thing is a product, make sure that I use the product rule. Remember, all rules are still in full effect. That includes chain rule, product rule, quotient rule, etc., etc. Okay, so here we go. Plus, now, if I think of this as 4x times y, the derivative of the first, the derivative of 4x is 4 times the second as it stands, plus the first times the derivative of the second. Well, the derivative of the second is the derivative of y, but notice that and that don't match up. So I'm going to take its derivative, but I have to leave that dy over dx footnote. You see that? Minus, what's the derivative of 3y squared? Well, it ain't an x, so I got to leave a note. But first things, let's write this as -6y dy over dx. And this equals, well, what's the derivative of a constant? 0. I will tell you that a very common error with students, and I'm not entirely certain why this is. I don't know if it's a function of laziness or it just happens all the time. I've had very unlazy kids make this error, is they'll forget to take the derivative of the constant and they'll leave that 1 over there. So be careful. All right, now remember, the whole purpose of this is to be able to solve for a derivative. At the end of the day, I want dy over dx. That means there is a derivative of something. So I'm going to get dy over dx by itself. So the first thing that I'm going to do is I'm going to send 2x plus 4y to the opposite side, and I'm going to gather my dy over dx's. So this is going to be 4x dy over dx minus 6y dy over dx is equal to negative 2x plus 4y. I could have also just as easily written that as negative 2x minus 4y, but I don't know why I did what I did, but I like it. All right, I'm going to factor out a dy over dx because that's the thing I need to solve for. That gives me 4x minus 6y is equal to negative 2x plus 4y. And then dy over dx is equal to negative 2x plus 4y over, respect I negative, right? You got to have those parentheses or all heck is going to break loose, over 4x minus 6y. Now, if I wanted to, I could factor out a 2 and cancel those and do all kinds of things. But really, who cares? It works. Whoop. I have taken a derivative, and it works swimmingly. So swimmingly, in fact, I had to take a drink. All right? However, I want you to notice again, this guy, not a function. This guy, not a function. To make this derivative work, I have to have a point. I have to have an x and a y, as opposed to this guy over here, where this is a function, and I only needed an x value. So what implicit differentiation does is it allows you to be a little less certain in terms of your curve. Your curve doesn't have to be a function. It can be a simple relation. However, for a trade-off, it says, okay, you can have a curve, my friend. However, you are going to need more information to make the derivative work for you. Now, remember that this right here, this was one of our earliest definitions of derivatives, wasn't it? And you may say, that Ridley, this is voodoo. This is madness. What are you doing? Well, believe it or not, we've been doing this all along. Let's say, for example, that I have y is equal to 3e to the x plus 5x squared. And I want to take the derivative. I want to find y primed, which is equal to dy over dx. Do you agree? So this is going to equal, question mark. Well, watch. If I differentiate with respect to x, well, what happens? Now, I don't have to use implicit differentiation. I'm simply showing you that you can use implicit differentiation, and you'll get the same thing that you had before. What's the derivative of y? 1. But I took a derivative as though it were an x, so I write 1 dy over dx is equal to 3e to the x plus 10x. And ta-da! I can get rid of the 1, right? It's just an understood 1. So dy over dx, which is equal to y prime. I'm allowed to say this is y prime. I can say this as f primed of x, because this, the thing we started with, was a function of x, or is a function of x. So that's pretty crazy. And these do take sort of getting your brain wrapped around how they work. They really do. But they're pretty fun, and they're not very difficult after you get used to them. And they show up relatively often. So you got to be a little bit careful. Now, what I really want to show you here is I'm going to show you probably the most important thing. Why does it do that? That's so crazy that it does that all of a sudden. I wonder if I can get it back. Go on a little voyage with me, would you? Nope, I guess we're stuck with this crazy little thingy-dingy for a while. Once we have implicit differentiation, we get to use it as a tool. So for example, watch this. What are we missing as far as our derivatives are concerned? Quick review. What do we know? Well, we know x to the n. We know a to the x. What else do we know? We know trigs, right? We know all of our trigs. That's pretty cool. We know chain rule. Chain rule, right? What else do we know? Am I missing anything thus far? Well, you may note it. Well, we know derivatives of constants. We know the ones that we've memorized, right? Square root of x, root x, 1 over x, etc., right? However, we got some pretty big gaps here. We're still missing logarithms, which we'll talk about in further sections. We're also missing derivatives of inverse trigs. So derivatives of inverse trigs, right? So if I have y is equal to the inverse sine of x, and I want to take its derivative. Now let's remember what that looks like. You remember what the inverse sine of x looks like? You remember? Right? All right, so remember, inverse sine of x comes from sine. So what it looks like is, instead of, remember, sine looks like that, and remember, inverses are symmetric across the x-axis. So inverse sine looks like this. It's a really short function, right? So instead of, remember on sine, we would go to what, pi halves comma 1. This is now 1 comma pi halves. This is still 0, 0. Remember, all I'm doing is taking x and y and flipping them. Excuse me, this is negative 1 comma negative pi halves. And that's what this guy looks like. And remember that it only goes from the range of the inverse sine of x is only from negative pi halves to pi halves, which is made obvious by this graph. And we use inverse trigs all the time. So we should probably be able to take their derivatives. Well, watch, we're going to be able to do that. Because there's no trick I can do here algebraically right out of the gate, because all I know is a derivative of a trig, and then I know my x to the n's, I know products, and I probably should have added products and quotients, etc. And what am I going to do? Oh, wait, I know the derivatives of trigs. So let's check this out. I know that y is equal to the inverse sine of x if and only if the sine of y is equal to x. Now remember, at the end of the day, if I start with this, all I know I will be done when dy over dx is solved for. So what am I going to do? I'm going to differentiate with respect to x. So the derivative of the sine of blah is going to be the cosine of blah times the derivative of the blah. Well, the derivative of the blah is 1 dy over dx, right? I have to leave that footnote. And you may say, whoa, Ripley, why didn't we have to leave like a dy over dx when I took the derivative of sine? Well, because sine's not a variable, sine's an operator. Sine is a go to the. There's no variable associated with that. The angle is where we get into trouble here. All right, but I'm getting beside the point. So derivative of sine of y is cosine of y, and then this dy over dx comes from that little understood 1 when I take the derivative of the y as though it's an x. And this is equal to 1, because the derivative of x is 1. All right, you with me? Okay, so let's look closer. I've got dy over dx is equal to 1 over cosine of y. Uh-oh. Well, that's no fun, because we know we started with a function. That guy is a function. That thing is a function of x. This is not a function of x. So however are we going to do this? Well, don't I know that cosine of y can be written as 1 over the square root, 1 over cosine of y can be rewritten as 1 over the square root of 1 minus sine squared y, right? True? Hopefully everybody agrees. That's our Pythagorean identity, rule number 1, right? That was the first one we ever learned. And wait. What's sine of y again? Oh, it's x. Isn't that awesome? This becomes the square root of 1 minus x squared in the denominator. So the derivative of the inverse sine is 1 over root 1 minus x squared. Now, I'm not going to run you through exactly the same process, but I am going to give you, how about y equals inverse cos of x? Well, it's exactly the same thing. Y prime, I would go through the exact same process. Y prime, I could write it as dy over x. I could write it as f prime of x, etc., is just negative 1 over root 1 minus x squared. Now, I am going to do inverse tan because it's a little bit trickier. Okay, let's change my color. Maybe that'll give me my dot back. No, Ripley didn't get his groove back. How about y equals inverse tan of x? All right, same problem, right? Same problem. We know what inverse tan looks like. Remember? That guy goes like this. It's got horizontal asymptotes at y equals pi halves and y equals negative pi halves. It's just tangent turned on its side, flipped around so that it's symmetric across y equals x, and you're done. All right, so what I'm going to do is I'm going to use the same trick. And implicit differentiation is a heavy-hitting trick. It lets us do a lot. Because otherwise I'd just be like, okay, this is true if and only if this, and now what the heck am I going to do? Well, remember, I know what the derivative of tangent of blah is. So it's kind of like if we're allowed to have chain rule, then we have to be able to take derivatives with this using some sort of algebraic mechanism. So the derivative of tangent of blah, hopefully by now you have memorized, is secant squared blah d blah. The derivative of y is 1 dy over dx. That's my footnote. And then this is equal to, well, what's the derivative of x? It's 1. So dy over dx is equal to 1 over secant squared y. Now we're back in the same problem that we had over here. This thing is a function of x. This thing is a function of x. This thing is what the heck is that thing. However, if I remember, if you recall, that 1 plus tan squared theta is equal to secant squared theta, another one of the Pythagorean identities, pretty easy to get to from sine squared plus cos squared equals 1. You just divide through by cos squared, and you get this other Pythagorean identity. Well, look close. Can't I simply rewrite this as dy over dx is equal, I don't know why my handwriting gets worse when this thing's this little cross, but it is what it is. This becomes 1 plus tan squared y. And guess what tan y was? Oh, x. So this is 1 over 1 plus x squared. This derivative shows up over and over again. You have to know the derivative of inverse tan and the derivative of inverse sine. Inverse cos and inverse cotan, not so much. If y is equal to the inverse cotan of x, then y primed is equal to negative 1 over 1 plus x squared. Okay? Now, I'm not going to go through it because now you can see the trick. It's pretty simple. If y is equal to inverse secant of x, then dy over dx is equal to, this is kind of a fun one, but maybe you could do this thing on the side, or maybe for some extra credit if you can convince your mean and nasty teacher to do it for you. This is x, it's 1 over x times the square root of x squared minus 1. Likewise, if y is equal to the inverse cosecant of x, then dy over dx is the same thing as the derivative of inverse secant, only it's got a negative. So this is negative 1 over x root x squared minus 1. Hey, we're starting to fill in some gaps now. The messing around's pretty much over. And implicit differentiation gave us the ability to do this. So now not only can we take the derivatives of equations that aren't functions, which is rad, but we can also use implicit differentiation in other ways. Down the road, I'm going to show you how to take the derivative of logarithms. That's kind of a big one that we're missing, right? Because look at what we got. We got 8 to the x's, we got trigs. Now we got all 6 inverse trigs. Again, you might want to put these on a vocabulary, like on a flashcard. Not a bad idea. So the only other big function that we're missing that isn't some other combination of other functions is the logarithms. Maybe we'll get to that in the next section. Until then, have a wonderful day, and I'll see you in the next section. Bye.